Hi everyone, let me share my screen. Let's see, start screen share. Cool. So I actually just gave this talk, but Google Hangouts did not record my screen share. So this time, out of an abundance of caution, I'm going to not enter full screen mode and just scroll through the slides and look in the background every once in a while to see that YouTube is in fact getting this. So anyway, I'll be talking about algebraic databases. So this is a talk that's meant to describe some of the content in the algebraic databases paper and in the equational formalism paper, which you can find on the categorical data website. And these slides are slides that I'll be giving in a little while, and also that I gave on a workshop for algebraic specification. So anyway, my goal here is not to reiterate all of the content of the other lectures on the YouTube channel, but basically to talk about how you can use the technology of algebraic specification to talk about functorial data migration. So just as a review, David Spivak a few years ago proposed using something called the functorial data model to solve data migration problems, and their schemas are categories and instances are set-valued functors. And that's kind of a semantics first approach to functorial data migration. And algebraic specification is sort of a syntax first approach. It's based on logic, and in this talk I'll be showing sort of the logic side of what's happening in functorial data migration. And this algebraic approach is also the approach that's used in the newer versions of the FQL tool, and that's being commercialized by the company. So start with a review of algebraic theories. So this lecture is obviously, it can't be a comprehensive introduction. Algebraic theories, which are also known as multi-sorted equational theories, are a foundational concept in computer science, and there are plenty of good textbooks on them. I'm partial to John Mitchell's text, but anyway, the basic idea is that you have these things called signatures, and a signature consists of a set of sorts. So the set of sorts, each element in it is called a sort, and you have a set of function symbols, and we usually write the sorts as these s's and function symbols using f, and each function symbol has an arity, which is to say it has a list of sorts that you can think of as its domain and a single sort that you can think of as its codomain. So for example, we might have a sort natural numbers, in which case the function symbol for addition would be natural numbers times natural numbers to natural numbers. A context for a particular signature is just an assignment of variables to sorts, and a term is basically what we can write using variables and these function symbols. So in particular, a term is either a variable or a function symbol applied to some terms such that the typing works out. So these sorts that are assigned to the function symbols can be thought of as typings. And an algebraic theory, which is to say a equational theory in a particular schema, is just a set of equations between terms of the same type. And we implicitly universally quantify over all these equations. And we say that the set of equations is a theory. And there is an entailment relation between equations. So what that means is that the theory says when two terms are provably equal or not, and provable equality is defined inductively using these inference rules, which are completely standard. So for example, the first rule, t equals t, is the reflexivity of equality. It says that any term t is equal to itself in any context. And then we also have rules for symmetry, that's the second one, and transitivity, that's the third one. We can also add variables to context, and then finally we have to make sure that the rules are closed under substitution. That's the last big rule there, and then that's it. That is the entire apparatus of equational logic. So suppose we have two theories, theory 1 and theory 2. What does it mean to have a morphism between them? Well, that means that we have a morphism of the signatures underlying the theory, which means that we have a function f that takes the sorts in the first signature to the sorts in the second signature, and then we take each function symbol in the source to a term, an open term, a term with variables, in the second signature, in a way that's compatible with the assignment of sorts. So if you have f going from s1 times s2 to s, then that would go to an open term of type f of s1 times f of s2 to f of s. And then to have a morphism between the theories on those signatures is that provable equality must be respected. So that means if you have term 1 equals a term 2 in signature 1, in theory 1, then you should have f of t1 equals f of t2 in theory 2. And then there is also a notion of a model. So we have these theories which are just equations. What does it mean to have a model? That is to say, a structure that satisfies the equations. Well, these are called algebras in the literature. That's where algebraic theory comes from. So if we have a signature sig, then an algebra for it gives for each sort S a set, which we usually call the carrier for that sort. And then for each function symbol, we have to give a function between the carriers that has the appropriate arity. And then we just say that a model of a theory is an algebra such that when we look at the meaning of each term and we look at the meaning of, we look at the equations in the theory, that when the theory says two terms are provably equal, then the model says that the two terms have the same meaning in that model. And then there is a notion of morphism between algebras and morphism between models that's completely standard. So obviously that's not a complete introduction to algebraic theories, so let me just mention the key properties, why we use these things for functorial data migration. So key property number 1 is that entailment is semi-decidable. That means if two terms are equal in a theory, then we can eventually figure that out. Entailment isn't outright decidable, which means that that process of figuring that out might run forever. We can't stop it. We can't decide yes or no if two terms are equal, but given enough time, we can always figure out if they are equal. And deduction is sound and complete. That means that if we have a theory and two terms are provably equal in it, then for every model of that theory, the two terms will denote the same element. So we can use provable equality as sort of a stand-in for equality in all of the models, which is an extremely useful theorem. And then finally, this is a bit more, concerns us more from the algebraic databases. The databases perspective is that every theory has something called a term model, which is a model that you can build out of the syntax of the theory itself that is minimal. So you take this term model, and if you have another model, there will always be a unique morphism from the term model to the other term model. And we'll be seeing a lot of examples of that here in just a minute. And fortunately for us, building these term models is also semi-computable, which means that if a theory has a finite term model, then given enough time, we can build it. And then the connection here with category theory is that these algebraic theories, these equational theories, are presentations of Cartesian multi-categories. And Cartesian multi-categories are equivalent to, but not equal to, product categories. So you can kind of think product category for everything here. Okay, so now onto the new material. What are algebraic databases? Well, we start by defining something called a type side. So a type side is just an algebraic theory, and we call its sorts types. And the idea here is that a type side is an algebraic theory that will represent an ambient computational context within which we are doing functorial data migration. So for example, here's a type side that we'll use in the talk. It has types, that is to say sorts, natural numbers, characters, and strings. Some symbols, so 0 is a zero-ary function symbol of type nat. Successor takes natural numbers to natural numbers, and addition, or plus, takes two natural numbers to a single natural number. There are 26 characters, A, B, C, and so on through Z. And then to build strings, what we do is we have lists of characters. So we have the empty string nil, and then cons takes a character in a string and gives you back a string. And then, of course, we have some equations. So in this case, we have equations that define what addition is. So it says for any x, any variable x, which will have type nat, sort of implicitly, if you add 0 to x, you get x. And for any natural numbers x and y, if you add the successor of x to y, then that is the same as the successor of adding x and y. So these equations are actually a very particular form. They're a program. They're an orthogonal term rewriting system, but in any case, they are just equations that say what the intended meaning of plus is. All right, so now what happens? Well, we have schemas that extend these type sides. So a schema extends a particular type side with new sorts, which we call entities. New unary function symbols that take entities to types, we call these attributes, as well as unary function symbols that take entities to entities, we call these foreign keys. And then new unary equations, which is to say equations that have a single variable free that has entity sort. And these definitions may seem kind of ad hoc, but in fact, they're set up in such a way as to recover functorial data migration from them. So if you change these definitions, then some of the properties of functorial data migration, like the adjointness of the data migrations, goes away. So that's the motivation for these particular kinds of definitions. So what is an example of this? Well, here's a schema. It extends the type side we just showed. It has two entities, employees and department, abbreviated emp and dept. The foreign keys are manager, that takes employees to employees, works in takes employees to department, and secretary takes department to employees. The attributes are dname and ename. Those are the names of the departments and employees, respectively. And then there's three equations, which are probably familiar to people who have watched the other lectures. So equation 1 says that the department that an employee works in is the same department as the manager of that employee works in. Equation 2 says that each department's secretary works in that department. And equation 3 says that the management hierarchy is only 2 levels deep. So, what are instances on these schemas? Well, an instance on a schema S is, as before, it's just another equational theory. We have new function symbols that are zero arity, and these can have entities or types. So the ones at entities we call generators, and the ones at type we call labeled nulls or Scullum variables. And we also have some new non-quantified ground equations. So what's an example of that? Well, here's an instance on the employee schema. It has 3 generators, A, B, and C, of employee entity, and 2 generators for department, M and S, and then some equations. So in particular, the name of employee A is Al, where Al is the abbreviation of cons of A, cons of L nil. And then there's some other facts here, like C's name is Carl and A works in department M. But the thing to note here is that this is just a random set of equations. There's not this set of equation, it's missing some information about managers, for example. There's nothing in these equations that talks about managers. So when we build the term model for that theory, in other words, when we consider that theory as a set of database tables, that's sort of the point of having these theories in the first place, is to have tables, database tables for them. That means that these tables are going to contain nulls in them, which in this mathematical framework means that there are terms in these tables that are built from other terms that aren't equal to things in the type side. So to elaborate on that, let's start with a department table. It has 2 rows. These are correspond to the 2 generators, M and S. So you can think of the ID column. Well, it's literally the carrier for the term algebra. So here the terms that are the carrier are M and S, and those came directly from the theory. And you can see that the secretaries for M and S in the table are exactly the same as the equation said. So we had an equation that said the secretary of M is B, and there in the table, the secretary of M is B. Note, though, that the department name for S is actually D name of S. So in the equational theory, we didn't actually say what the department name for S was. So that means in this term model, the thing that goes in that cell is a term, D name applied to S, that we can think of as being a kind of null. But it is a null that captures some information about the lineage. So it's, in particular, we know that it's D name applied to S. So let's now look at the employees table. So here there are 6 rows. We have the 3 employees that were the generators, A, B, and C. Then we also have their managers. So I mentioned that the equations didn't say anything about managers. And what that means is that the term model, each employee has to have a manager, because manager is a function from employees to employees. So here there's an employee called the manager of A. And luckily for us, we had the equation that says manager composed with manager equals manager, which means that each employee has a manager, and then that manager is himself. So this is a finite table. If we didn't have that manager composed manager equals manager equation, then this table would be infinite. But here too we see some terms that are equal to things from the type side. For example, the name of employee A is Al, but we didn't specify a name for employee B, so its name is given by the term E name of B. And so this instance you can think of as a set-valued functor, and it is a set-valued functor from the schema, where we can consider the schema as a category because of all the unary restrictions. But anyway, the instances are these term models, and this is how we recover a connection with functorial data migration from algebraic theory. In particular, what does functorial data migration look like? Well, suppose we have 2 schemas S and T on the same type side, and we have a morphism between them, that is to say, a schema mapping. And moreover, that mapping is the identity on the type side. So that's what we mean by a schema mapping, or a morphism of schemas. And it's important, this identity on the type side part. And the schemas on a type side form a category. Similarly for instances. So here, instances, recall, these are just equational theories. They have a meaning as the tables, but instances are defined to be theories, and the morphisms between them are morphisms of theory that are the identity on the schema S. And with this definition, we have that the instances on a schema S form a category, S inst. And then finally, we can define the data migration functor. So suppose we have a schema mapping, f taking s to t. Then here we define sigma f, which goes forward, takes s instances to t instances as substitution. And then delta is its right adjoint, and pi is delta's right adjoint. So this part is a little bit different than the earlier work in functorial data migration, where we're working semantically. What we do is we define delta to be composition, and delta has a left adjoint sigma and a right adjoint pi. But here it's sigma that is the easy one, and it's defined as substitution. So what's really happening is that by working syntactically with equational theories, we have an easy sigma, and the earlier work on functorial data migration, by working semantically with set-valued functors, it had an easy delta. So you can sort of pick which world you want to live in, syntax or semantics, and each one will have one of the data migration functors being easy, and then we'll define the other two as adjoints. And of course, as adjoints, these data migration functors are only defined up to unique isomorphism, which you can think of is meaning that the IDs in these database tables are meaningless, or thinking syntactically, you can think of as saying that instances that have exactly equivalent provability power will be interchangeable in any context. So we'll see some of that as I describe what delta, sigma, pi are like. And to do that, I have to introduce this graphical notation for schemas. So this will be familiar to people who have seen the other lectures. Basically, this is a notation for just schemas that ignores the type side part of the schema. So in particular, schemas consist of foreign keys and attributes. And in this notation, we draw the foreign keys as directed edges, and we draw the attributes as the open circles, and the equations become path equations. And this is something called ER diagram notation. And I'll describe what these delta, sigma, and pi look like using this notation, and also using tables, using term models rather than on the equational theories, because it's kind of easier to understand the meaning of these things when working with tables rather than big sets of equations. So anyway, here is a schema mapping F. It takes a source schema that has two entities, N1 and N2, to a target schema which has one entity, N. So it, in particular, it maps both of those entities, N1 and N2, to N. And then it maps the attributes straight across, name to name, salary to salary, age to age. And the delta functor goes backwards to the direction of the schema mapping. So if you start with this instance on the right, N with 3 rows, then you find that the delta functor projects, it splits up that table into 2 tables, each of which has 3 columns. And as I remarked before, we should think of the IDs in these tables as being meaningless. So I've deliberately changed the IDs between the tables to demonstrate that IDs are meaningless, but the attributes themselves are not. So Alice, it matters that Alice in N1 is the same Alice that is in N, and the reason we have that is that we require these schema mappings to preserve their type sides, which means that as you translate from one schema to the other along F, you always send Alice to Alice, even if you don't send ID1 to ID1. All right, pi is the next data migration functor. So here we have done the same schema mapping. It takes N1 and N2 to N, and here pi goes in the same direction as the schema mapping, and so here we have 3 rows in N1, 3 rows in N2, and we get 9 rows in N. It just does a Cartesian product, and the reason is that there is no edge between N1 and N2 in the schema. There is no foreign key. And finally, what does sigma look like? Well, in this particular case, sigma looks like a kind of outer union. So at the level of syntax, sigma is actually given by composition, but sigma is given by substitution, but when you're working at the level of tables, it's kind of hard to describe what it's doing. It's something called a left-con extension, but in any case, we have the same schema mapping as before. N1 and N2 go to N, and the attributes go across. And we have these two tables on the left, which are not union compatible. They have different attributes. And so sigma outer unions them together, and here we've written null1, null2, null3 in the table just to abbreviate terms like age of A, age of B, and so on, because those terms are a little bit too big to fit on the slide. So this is just another reason you can think of these terms that are not equal to things in the type side as being kind of null, labeled null things. All right, and finally, what happens if there's a foreign key between N1 and N2? So here we call the foreign key F, and in the instance on the lower left, we have that F maps straight across to N2. And what happens here is that pi and sigma both do a join, and then delta does a project that sort of remembers how the projection was done by writing it down in F. So very natural operations, and these are exactly the same as they were in earlier work on functorial data migration, but now we can recover these from operations on algebraic theories. And as before, certain kinds of functorial data migrations, those that have this special triplet form, a pi, then a delta, then a sigma, that have some restrictions on the mappings involved. There's a theorem we proved that says that the data migrations of this form are equivalent in expressive power to the select project product union fragment of the relational algebra. And in addition, the sigma operation has a semantic similar to something called the chase, which is how we can use it to do data integration, which I haven't really talked about in this talk, but there's another talk that mentions it. And then there's also nice for-where return syntax that you can use to specify these data migrations, which I won't talk about here because they're in the other talks. And also there's other cool stuff you can do. Pivoting turns instances into schemas and vice versa, and it all has a nice way to talk about it using equational theories. All right, so I'll conclude this talk with the final bit, which is about how this formalism for algebraic databases compares with another formalism for describing databases in query known as LINQ. So LINQ stands for Language Integrated Query, and it's basically a way to take a programming language, say Java or Lambda Calculus or Haskell, and add to it a notion of schema, query, and instance, usually using monads and comprehensions. But the basic idea in LINQ is that collections are terms of set type or list type or bag type, and that in our approach, in this algebraic database approach, we call it a Kinnel approach, where Kinnel is LINQ but backwards, sort of. We say that collections are actually types. So we said before that employee was a sort in an algebraic theory. That's basically the same as saying that it is a type in a programming language, and that these foreign keys are actually first-class functions. So there's a big difference type theoretically between these two approaches. Do you want to represent collections as terms or as types? And they have different computational properties, and the LINQ approach is more popular, but the Kinnel approach you can find in independently typed languages like Coq and Agda. And in particular, we can think of Kinnel as being kind of a one level up version of LINQ. So what do I mean by that? Well, in LINQ, a schema is essentially a collection type over the base type. So for example, we can think of a table with two columns, an int and a string, as being a set of ordered pairs. And an instance then would just be a term that has that type. So here the term is 1CS union 2 math. That's meant to suggest the table with one department number 1 called CS and department 2 called math. And then data migrations are just functions which can be expressed as terms. So here the projection function takes a set of integers and strings and just returns the integers. So you can think of that as projecting off from this table just the department IDs, for example. So in Kinnel, it's one level up in the sense that a schema is no longer a type, but it's an entire type theory. So we add a sort called department, and then we add a function symbol called name that takes department to strings. And then an instance is no longer just a term of a particular type, but it's a term model of an entire type theory. So for example, in this term model, we have terms D1 and D2. These are departments such that some equations hold, and we get an entire model. And then finally, the data migrations, rather than just being functions, are entire functors. So here we can use delta to take an instance on the schema that has department and name to a schema that just has department. So it's kind of a projection forgetting kind of thing. And so for this reason, we think of Kinnel as being one level up. All right, so this is the point in the talk where I usually show the FQL tool, but seeing as how that's been described in some previous talks, I will just conclude by saying that I presented a formalism based on equational logic, based on algebraic theories for specifying and manipulating databases and queries. And it's the basis of the FQL tool, and there's a bunch of papers, well, 2 papers, Algebraic Databases and the equational formalism paper that you can get to from our website, cadinf.com. There's all kinds of interesting things going on here that I didn't talk about, like there are connections with automated theorem proving, and these things called institutions, which are like categorical notions of logics and conservative extensions and all kinds of cool stuff. So anyway, thanks everyone. I believe that YouTube did in fact capture this video. So I will stop it now, and thank you all again.